before we can do any actual examples, we have to establish three fundamental concepts in radical algebra. The first of these is known as reducing radical terms or just reducing terms. A term, by the way, is a non-radical times a radical, and that's what we mean by a single radical term. By the way, before we reduce this term, it's worth noting that sometimes we put the time sign in between the whole number and the radical, and sometimes we don't. And you have to be flexible about not demanding that you see the time sign all the time, because you probably won't. But back to this problem. Radical 72 is clearly a decimal. There's no whole number times itself that equals 72. Nonetheless, we would deal with expressions like this in algebra all the time, and we want ways to reduce them. And what does reducing mean? Well, it means to make the number inside the radical, also known as the radicand, smaller. So how can I make the number under the radical, or the radicand, smaller here? Well, I'll show you a trick. What you can do is take this radical and factor it. It just so happens that 36 times 2 is 72. We're using something called the multiplicative property of radicals here, or in short, radicals multiply, or can be factored to reverse the process. Now, once we've gotten it in this format, we can take radical 36, recognize that, oh, that's a whole number. Radical 36 is 6, because of course 6 squared is 36. And once we simplify the radical in that way, we can multiply the whole numbers together. 5 times 6 is 30, and we now have a simplified radical expression. What makes it simpler? Well, the number under the radical, or the radicand, is smaller, and we value that in algebra for whatever traditional reasons, and that's what we mean by reducing a radical term. By the way, if you were wondering, back when we factored 72 into 36 times 2, if it crossed your mind that there are other ways to factor 72, then good thinking. Watch as I do this problem a different way. Suppose instead I had factored 72 into 9 times 8. Let's examine what would have happened. Radical 9 is 3, and 5 times 3 is 15. Well, that doesn't look like the same answer. But it turns out all three of these expressions, the ones at the bottom of each column and the original expression, are all the same. Now, 15 radical 8, it turns out, can be simplified further, because after all, I can express radical 8 as radical 4 times radical 2, but radical 4 is 2, and now I can multiply the whole numbers. 15 times 2 is 30, and thus showing that even if I had chosen a different factorization in the beginning, I would have got the same result in my final reduced form of this term. So that's fundamental principle number 1, reducing terms. Fundamental principle number 2, multiplying terms. Suppose I were to multiply these two radical terms together. Now, of course, each one of these radical terms can be expressed as a decimal in its own right, but the traditions in algebra have us avoiding decimals to see how we can simplify expressions without decimals or calculators. So in that tradition, let's see what we can do here. Well, one thing I could do is realize that this is really just the product of 4 numbers. And as such, I can rearrange the order of multiplication. That's called the commutative property of multiplication. And furthermore, I could multiply the whole numbers together and the radicals together, thus expressing this as 21 radical 30. So when we say we're multiplying radical terms, that's what we mean. Essentially, you multiply the whole numbers together and the radicands together. Which brings us to fundamental principle number 3, combining like terms. Here's an example. Now in this particular problem, you'll notice there's 3 multiplications. They're not written, but there's 3 multiplications and 2 additions. And generally speaking, multiplication comes before addition. But since I'm not interested in using the decimal equivalents of radical 2 or radical 3, which I could do if I wanted to crunch this entire expression down into 1 decimal, then there's no way to perform those multiplications. But here's an interesting trick. What if I rearrange the order of the terms? What if I took the first and last terms and put them together? Well, we know we can rearrange the order of addition, and that's another commutative property. And so by doing so, I can employ an interesting trick. Notice the first 2 terms on the left of the bottom expression. You may see them in red. Both of those terms have a factor of radical 2. Using the distributive property, I can factor out a radical 2. I could have written it in front of the parentheses as well, but tradition dictates that I write it afterwards. Not that that matters. The important point is that once I've factored a radical 2 out of those expressions, I can simplify the 4 plus 7, and that ultimately gets me to 1 term with a radical 2 instead of originally 2. And by rearranging the terms in their order and using the distributive property, we can combine like terms and simplify the expressions. Now, none of these are necessarily problems that you would encounter on your own in an algebra course, although you might in the easy cases. But each one of these 3 fundamental processes is going to be the basis for some more complicated examples that we're going to see in the remaining part of this video. So let's take a look at our first example of many, as you can see here. Sometimes when students look at radical expressions, they just see a bunch of weird-looking symbols and don't know what to do first. One of the most important skills you can have in radical algebra is to try to imagine an expression that is simpler but has the exact same format as the one that you're analyzing. If you look at the algebra problem on the right, your algebraic intuition might tell you to distribute the x into the parentheses. In other words, to multiply x times y and x times z. Well, if that's your algebraic thought, then follow that same logic when doing a radical problem. When one sees this problem, one should think, I'm going to distribute what's outside the parentheses into the parentheses. Now this turns out to be the result, and let me explain. First I multiplied the 3 radical 2 times the first term. Hit pause if you want to analyze this. Here are the particular details. Next I multiplied the 3 radical 2 by the radical 2, and I got 3 radical 4. Here are the particulars. Now one might think that we could stop here because we have 2 expressions and there's no way to factor out a radical because they're different. But the challenge of the 3 fundamental processes that we saw in the beginning of this video is that you have to employ them strategically throughout these problems to try to get a more simplified expression. So while you may be tempted to quit here, it turns out we can go further. Let me explain each term. 15 radical 12 simplifies to 30 radical 3. Why is that a simplification? And how did I get it? Well, why is it a simplification? Because the radicand is smaller. How did I get it? Here are the particular details. I used the fundamental principle of reducing terms. Hit pause if you want more time to analyze this. Similarly, I reduced 3 radical 4 to 6. Here's the details. And now that I've reduced the radicals as much as I can, I have no like terms to combine. There's nothing else I can do to simplify this expression. Now I'm done with this problem, but there's a noteworthy comment about the problem and the answer. I worked out the problem and the answer on a calculator here, and both of them worked out to 45.962, approximately. So why am I bothering to take the top expression, whose decimal value is 45.962, and simplifying it to the bottom expression, whose decimal value is also 45.962? Well, that's the tradition of algebra. We take symbols and manipulate them into easier or more recognizable symbols. And that's a tradition that you need not only in algebra, but to go further on in mathematics courses. That being said, let's move on to the next example. Suppose we wanted to do this problem. Again, sometimes you can look at these and see so many radicals that it seems like a nonsensical expression, and there doesn't seem to be any clear indication on what to do. Well, imagine that without the numbers or the radicals, that we had an algebraic expression of similar form, as you can see here. Well, if you had an algebraic expression like this, you would try to combine like terms. So I'm going to focus on that here. There doesn't seem to be any like terms in this expression. After all, the radicands are all different. We can only combine like terms if the radicands are the same, using the distributive property by factoring that radical out. But what you may not have noticed right off the bat is that 4 radical 24 is simplifiable. So how did I get 8 radical 6? Using fundamental principle number 1, reducing. Hit pause if you want the details. And by changing the radical into a lower radicand, I've not only simplified the problem, because 6 is less than 24, but also I happen to notice that I have 2 radical 6 terms in this expression. And because I have 2 radical 6 terms, I can put them together. It doesn't matter where. But by putting them together, I can factor out a radical 6 here, which ultimately will lead me to this as my final simplified expression. Here are the details on me factoring out the radical 6. So again, we're not solving equations here. We're just manipulating symbols to make less symbols. That's called simplifying, and it's a very important skill in algebra. Now let's take a look at another example. So again, this may look like a bunch of radicals crammed into a confusing expression. But if you stop and think about what's happening here, think about this as an algebra problem without the radicals, then you quickly realize that this is just a FOIL problem, if that's what you are used to calling it. It's essentially a multiplication of binomials. And so we're going to use the same process here with the radicals that we would have if these were just algebra symbols. Now this turns out to be the next line. Let me explain each of these step by step. First, I multiplied the first term by the first term. You can pause for details. And that gave me 18 radical 5. Then I multiplied the outer terms. Pause for details. That gave me 3 radical 50. Then I multiplied the inner terms. Here are the details. It's worth noting here that when we have an expression like radical 2 times 6, we typically write the whole number first, so we would write this as 6 radical 2. Not that you have to. And that gave me this. And finally, the last term of each pair multiplied together gives me negative radical 20. Now I'm not done with this problem, but it's worth noting here that I've essentially used the FOIL or multiplication process, just like I would have in an algebra problem that had no radicals, to expand this expression. Now at this point, I wouldn't necessarily call this a simplification. It looks worse and has bigger numbers under the radical than the original expression. But it turns out there's more that we can do with this. For example, we can simplify 3 radical 50 into 15 radical 2. Here are the details. We can also simplify radical 20 into 2 radical 5, and the details are shown here as well. So now I've gotten the radicals smaller again, but one still has to question whether this is a simplification of the original expression. It doesn't look much simpler, but it's about to become so because I can rearrange the terms. Notice I have 2 terms that have a radical 5 in them, and I have 2 terms that have a radical 2 in them. So all I've done here is rearrange the order of addition. And in so doing, I can now get my final result here. This result, by the way, came from combining these 2 terms. Here's me using the distributive property to combine those, and similarly combining the last 2 terms, and there's the distributive property showing that as well. So as you can see, these problems can get quite messy, but they all come down to 4 basic ideas. The 3 fundamental principles that we saw earlier in this video, combined with your basic knowledge of algebra rules as they pertain to non-radical expressions. And if you combine those basic algebra rules with the 3 basic principles of radicals and keep simplifying till you can't go any further, you can simplify any radical expression that you're given.